Simple exponential growth and decay. Recall the simple exponential growth and decay formula. P equals A times e to the power of kt, where P represents the population or value at time t, where t is greater than 0. A represents the initial population or value at time t equals 0, or the start of time. K represents the growth constant, or the growth rate, where k does not equal 0. And t represents time. Now the derivative of p with respect to t is given by dp dt equals k times a times e to the power of kt. And this is found by differentiating this exponential function and then multiplying it by the derivative of the index. So the derivative of a e to the kt is just a e to the kt multiplied by the derivative of kt, which is just k, and so the k just appears at the front. Now notice that the derivative involves this term a e to the kt, and a e to the kt is just equal to p. So we could write dp dt as dp dt equals k times p rather than k a e to the kt. So we can see here that the derivative, or the rate of change of population with respect to time, is proportional to the value of the population at that point in time. So we could think of k as the constant of variation, or the constant of proportionality. Now this formula is useful for modelling population growth or any phenomena that decays to 0 as t approaches infinity. So for example, radioactive decay, half-life of medication, etc. Now when k is positive, p approaches infinity as t approaches infinity. So p is growing, it's getting bigger as time goes on. When k is negative, p approaches 0 as t approaches infinity. So this graph shows that particular situation. So with a negative value of k, starting at some initial value a, p approaches the x-axis as time, or t, approaches infinity. Now an extended formula is needed to model anything that decays to a non-zero value. So for example, a cup of coffee cooling down to room temperature.